Welcome everyone to this little discussion about the OWASP Top 10, specifically the 2021 version of the OWASP Top 10, how it is different from the previous versions, what is interesting and important about it to know. Before we start, just a little bit of an introduction about myself and Cydrill. So yes, my name is Balázs Kiss, and I have been working in cybersecurity for over 14 years now. I have participated in many commercial security evaluation projects of various products, from embedded systems and mobile phones to complex web applications. And I've also participated in quite a few European Union international research projects in the topic of software security. And kind of as the origin story, this is where me and our colleagues had the idea to eventually teach developers about secure coding and why it's important. Because during all of our work, and my work in particular, I have found that developers kind of kept making the same mistake over and over again. So basically, you would find, let's say, a SQL injection or SQL injection vulnerability in a web application. We would, of course, tell the software creator, the vendor, to fix the problem. But then in the next prototype, they would have the same problem again. So that is why we decided to sort of have a more structured way of informing developers about these typical mistakes and what to look out for. So yeah, I think that's a short enough version. So we have enough space for the actual meat of this little introduction into the application security and the OWASP Top 10. So let's get started. I think I will turn my camera off in the beginning. I will turn it back on at the end when we get to the questions, in case anyone has any questions, of course, so that I'm not distracting from whatever I am presenting here. So let's get started. But before we can get into an in-depth discussion about the OWASP Top 10, we need to discuss some basics and establish some baselines. What do we actually mean when we talk about software security? Now, we have, of course, all heard about all kinds of security incidents affecting everyone, from the smallest open source project to huge multinational corporations. Nobody is immune to these problems. They can happen to Google, Facebook, Amazon, whoever. Everyone is potentially exposed to these security issues. But all these incidents have one thing in common. The attackers, the hackers, always exploit some sort of weakness in the system. And most of these weaknesses are caused by programming bugs. And it's an unfortunate fact of programming that we can just never really get rid of all the bugs. Indeed, like Murphy's Law says up here, there's always going to be at least one bug somewhere in our system that we just can't find. So let's have a little bit of a simple illustration. So let's take a look at what I actually mean here. Let's say that we have as this black oval representing all of the bugs in our system. So I will type it out. These are the bugs. And of course, these bugs are things that we haven't found yet. A subset of these bugs, I'm going to draw a different sort of oval here, is going to be here in the center. And let's call this one vulnerabilities. Now, a vulnerability is, at its heart, a software bug which is exploitable in some way to the attacker's benefit and, of course, to our detriment. Unfortunately, we can't tell from the outside which bugs are vulnerabilities because we don't even know where the bugs are. So the only way to get rid of all the vulnerabilities is to fix all the bugs. And well, realistically, new bugs will keep appearing in the code as we add new features. And while most of these bugs won't be useful to the attackers, some can be exploited to break the security of the entire system. And we just can't get rid of these so-called vulnerabilities without fixing every single bug, which is not feasible in practice. So when we look at it like this, things look kind of bleak. Because, I mean, it looks like that we just can't solve this problem. We are always going to have bugs. Some of these bugs can be exploited and they can be used to break the security of our systems. Thankfully, the situation is much better than it first appears because about 90%, in fact, I would say even closer to 95% of these vulnerabilities, I'm going to draw another blob here. So it's like a shape like this, maybe. Yeah, let's say this represents all of the issues that are typical programming mistakes. So these mistakes can be identified relatively easily in code. And many of these mistakes are known, we know a lot of things about them. We know what they look like, we know how they can be exploited, and more importantly, we know how to protect against them. Many of these bugs have been around for a very long time, sometimes even decades, and there are numerous protections and mitigation measures for them available in a large variety of programming languages. In fact, I will make it even a bit bigger. Let's see, cover these parts as well. So even just taking care of these typical vulnerabilities will push you 90% of the way there. And this checks out if you look at the statistics. And the secure coding skills that you can pick up along the way can take care of the other 10%. So the parts that we didn't cover here, let's call it the blue part. Because if a developer is using secure coding techniques correctly, like defensive programming and input validation, they can make the rest of these vulnerabilities much, much more difficult to exploit and mitigate the consequences of successful attacks, and generally make the job of the attackers much harder. So that's basically the idea about secure coding, is we know about the typical weaknesses and how to protect against them, and we know how to write robust code that is secure against potentially malicious inputs to protect against the other vulnerabilities that are not in this typical category. For the most part, the bad guys are also rational actors. If we make it hard enough for them to find and exploit vulnerabilities, such as by getting rid of these typical common vulnerabilities, then they will look for easier targets. Here is a pretty relevant quote about this. So Bruce Schneier is a well-known cryptographer and security expert. He has a famous quote in this area. When trying to secure a software system, the goal is not 100% perfect security, but rather adequate security at a reasonable cost. In a game theory sense, this is what we call an infinite game, where the two players are the developers and the hackers. And the goal for us as developers is not to beat the hackers, but the goal is rather to stay in the game, no matter what the hackers try to do. So, with this in mind, let's get to the main topic of this talk. What is OWASP? What is the OWASP Top 10? And why is this useful? How can this be useful to us? So, the Open Web Application Security Project, or OWASP, is an international web application security community. Though lately they have been looking at the security of non-web applications as well. So they have several divisions that are dealing with things like IoT security and such. They have created many tools, documents, how-tos, and cheat sheets to help developers make more secure software. And all of this information that they have is free to read, access, and use. And all of it is quite useful. But their best known product, perhaps, is the OWASP Top 10. This is a list describing the 10 greatest risks to web applications that they publish every few years. Originally, they published it every year back in the early 2000s. But in 2004, they realized that maybe it is a better idea to switch to a 3-year cycle instead, which then became a 4-year cycle in 2013. So we basically went 2003, 2004, 2007, 2010, 2013, 2017, and 2021, which is now the latest version of the OWASP Top 10. Incidentally, the latest version of the OWASP Top 10 was released just now on September 24th to commemorate the 20-year anniversary of OWASP as an organization. So the OWASP Top 10 is perhaps the best known document when it comes to software security, and it's useful to many different people. It is useful for software developers because they can learn what are the biggest mistakes to avoid and how they can be avoided. They are useful for security experts because they know what weaknesses to look for when evaluating the security of a web application, and managers can also use it as a basis for software risk management. And of course, this list can also drive the business of companies creating security software because they can just make sure that they are focusing on the problems listed in the top 10. Which then, of course, leads us to an interesting question. Is this actually a standard? Can we consider the OWASP Top 10 to be a cybersecurity standard? And here's the thing. Just as with any top list, the scope of the top 10 is inherently limited. It is very, very useful for spreading awareness of the biggest issues, but it cannot ever be complete. You can and should use the top 10 to start the software security journey, and to know which issues need to be prioritized before anything else, because everything on the OWASP Top 10 is obviously a very, very serious problem that we always need to know about. You can think of them as the low-hanging fruits, basically. But the OWASP Top 10 should not be considered a software security standard by itself. If someone tells you that we are OWASP Top 10 compliant, you should at least be looking at them somewhat suspiciously for that. And this is true now more than ever, as many of the entries in the OWASP Top 10 are abstract problems. And specifically, quite a few of them are untestable, at least directly in automated ways. So if, let's say, for example, you want to cover the top 10 issues in your security testing processes, you should be using what is called the Application Security Verification Standard, the ASVS, which is a comprehensive document that covers all aspects of application security, all these issues that are mentioned in the top 10, and many more, using easy-to-use checklists that also fulfill the requirements of industry-specific requirements such as PCI DSS. But of course, the ASVS is a 71-page document, which is quite a little bit heavier than the top 10 list, which can fit into a single page. So in summary, the OWASP Top 10 is useful for awareness. It is useful as a starting point in training and figuring out what the problems are. It is also potentially useful when developing the system to try to identify particular issues. But in general, if you want a comprehensive view, you are much better off using the Application Security Verification Standard. So how is the OWASP Top 10 constructed? At its core, the top 10 is a data-driven view on the state of the art in software security. After all, it's supposed to talk about the 10 most relevant security issues. Specifically, 8 elements on the top 10 are selected by examining their incidence rate. So the frequency of at least one of the issues in the entry being present in the web application as reported by 3 different groups: application developers, so developers who are reporting the issues in their own code; security researchers who are reporting the issues they have found themselves in their research; and security product vendors who are reporting the issues that their tools have identified. The other 2 are selected by asking the OWASP community of security experts which weakness they think will be the most important and relevant in the upcoming years. So it's kind of a forward-looking view on potential issues, potential security issues. And of course, these 2 that are selected by the experts have to be issues that are not already in the 8. So if there is an overlap, OWASP just picks the next issue from the community list instead. But what do I mean when I say security issues? Well, the top 10 contains references to a vulnerability taxonomy called Common Weakness Enumeration, or CWE. So the CWE as a taxonomy has been around for a long time, longer than the OWASP Top 10, and it is used as the primary way to categorize software weaknesses. Each CW entry describes an individual vulnerability or design flaw that can be sometimes very broad, like trust boundary violation, which can mean a lot of different things, or it can be very, very specific, like cross-site request forgery, which is a very concrete vulnerability. The top 10 has always been integrated with the CWE to a certain degree, but in 2021, this had a lot of emphasis. This mapping is more extensive than ever. So if you compare to 2017 and 2021, in 2017, there were only 24 of these CWE entries, so these weaknesses, which mapped into the OWASP Top 10. But in 2021, we now have 193 separate entries. One of the entries on the OWASP Top 10 in secure design is actually containing 40 of these CWEs in itself. So if you look at it like this, the OWASP Top 10 is not really a top 10. It's much more like a top 193. So as we have just seen, there are some major changes in the top 10 in 2021. So let's look at them in more detail and look at what actually is on the top 10. So what we see here is an image that serves as the introduction of the top 10 document itself. And it's a pretty good way to see how the top 10 list is progressing and what has changed about it on a high level and a more specific lower level as well. We can see that there are 3 completely new items on the top 10, and some of the previous items have been also merged maybe into some of these categories. And we can also see that many of the names of these security issues have become much more general. Indeed, now we can see that the top 10 is described as a list of categories instead of individual vulnerabilities. So they actually changed the terms. Now we are not necessarily talking about a vulnerability when we look at, let's say, number 4 of the OWASP Top 10. We are talking about a category of problems. So we are now have 10 categories and not 10 specific issues. And this gets further enhanced when we look at the names of many of these names, because a lot of them are plural. You can see that we have one called cryptographic failures, which implies that there are many different kinds of failures that we are covering here. And we have similar ones like identification and authentication failures, for example, which is the renamed version of broken authentication. So basically, we can see that there is a shift in the, let's say, the concept behind the OWASP Top 10, and I'm going to talk a bit more about that. But for now, let's look at the more trivial changes before we go in depth about the really big ones. The biggest change we can notice is that broken access control, which used to be number 5, suddenly jumped to the top of the list. It is now considered to be number 1. So why did this happen? The answer is that this category contains many, many different problems, and the incidence rate of these weaknesses has become very high. And since this also encompasses a very broad sense of issues, a very broad category of issues, there are many, many, many ways how access control can be broken inside of an application. That is why it is now catapulted from number 5 to number 1. Let's look at sensitive data exposure, which has been renamed to cryptographic failures. So technically, the content of this has not changed. So it basically still talks about the same things it used to talk about before. Sensitive data exposure, meaning any kind of situation where information can leak from a system, confidential information or private information that we don't want the attackers to access. But now we are focusing much more on the causes of this, because sensitive data exposure was much more like a consequence of the problem, but cryptographic failures are the causes of what can result in sensitive data exposure. So yes, basically it's the same issue, but we have now changed the wording so that now we are talking about the causes of the problems instead of the outcomes. And this category is talking about all the different mistakes developers can make when using cryptographic functionality, like using the wrong random number generator functions, the wrong hashing algorithms, or giving wrong parameters to encryption functions. The next one is injection, and it used to be number 1. Now, injection is a specific type of vulnerability, a very serious type of vulnerability, where the developer makes a basic mistake when they are confusing the nature of data and code, and they are basically allowing bad input to potentially manipulate how data is processed. Now, this problem has fallen from number 1 to number 3 for several reasons. While injection vulnerabilities are very high risk, the incidence rate has decreased quite a bit. And you can also notice that number 7 on the previous OWASP Top 10, cross-site scripting or XSS, has been merged into injection. So it is now part of injection. And this is because cross-site scripting was basically a subtype of injection problem, only it was basically HTML injection that happened in the browser. Then we have, as the next category, security misconfiguration. Now, this is also a result of a merge of several categories, specifically security misconfiguration, of course, and also XML external entities, or XXE. So XXE was one of these very low-level issues, vulnerabilities that I mentioned in the previous version. And because this problem can happen if an XML parser is misconfigured, that is why it was merged into the misconfiguration category. And this category also contains some security topics that were previously perhaps discussed in different contexts, such as the security of cookie handling. But in general, any kind of issue that is related to incorrectly configuring some component goes into this category. Then the next one is vulnerable and outdated components. This was previously known as using components with known vulnerabilities, and it has now a much more descriptive name. Modern web application architectures depend so much on third-party code that the problem of vulnerable or outdated dependencies is likely to become an even more serious issue as time goes on. For example, in Node.js web applications, NPM is basically a minefield, and you generally don't want to stand on a mine when it goes off. Then, of course, we are skipping over cross-site scripting here. Then we have broken authentication, which has now been renamed as identification and authentication failures. And this has fallen quite a bit from number 2 to number 7. The reason for this is that much of this functionality, which is, of course, authentication functionality being incorrectly designed or implemented, is now taken care of automatically by web frameworks. So the developers can't really make mistakes as easily as they used to. There are many mistakes that these are automatically shielding the developers from. And finally, we have some new categories, of course, and we have security logging and monitoring failures, which is previously known as insufficient logging and monitoring. It has slightly moved up a bit, and this is a category which is halfway between secure coding and incident response, basically making sure that if there is any kind of security problem, it should be logged so that incidents can be later analyzed and audited to investigate potential breaches and identify their root causes in time, which is becoming much more important, unfortunately, because of how many breaches we have. But there are also these 3 completely new entries, number 4, number 8, and number 10. So let's look at those in more detail. The first one of these is number 4, insecure design. And this is perhaps the most controversial addition, because insecure design covers design flaws of various types, which is very different from the previous focus of the top 10 on implementation problems, so code problems. But it's true that security issues can and will be caused by design flaws just as easily as bugs. And catching these issues early is very, very important. After all, if the designers forgot to add authentication to a critical component, and you only discover this when the software is almost ready to ship, you will have to do a lot of painful and very expensive re-engineering work to make sure that this functionality is there and implemented. Not to mention that these issues are notoriously hard or even impossible, arguably, to test with automated tools. So what we need to do here is to follow a principle called shift left, which tries to identify and fix security issues as early as possible, which can be sometimes even in the requirements or design phase. So it's important to look out for missing controls, security controls, and security functionality by following the standards of security engineering for security requirements, so the confidentiality, integrity, and availability triad, and threat modeling, which is represented with STRIDE, or spoofing, tampering, repudiation, information leakage, denial of service, elevation of privilege. So I'm not talking about these in detail. This is just like some best practices that should be used in this category. And even more importantly, it is important to adopt some sort of secure software development methodology like the OWASP Software Assurance Maturity Model, or SAMM. And as a side note, this category also contains issues and solutions that are not on the web application side, such as the same origin policy in browsers. Now, also new to the top 10 is software and data integrity failures. This is number 8, which at first sounds a little bit odd and maybe redundant with some of the categories we have already looked at. But this one has a very important role in covering the manipulation of data. Think back to cryptographic failures, which was number 2 when we talked about the confidentiality of data. Here we are talking about the integrity of data. So that is one of the focuses of this category, but we are also talking about the integrity of code. So whether an attacker is able to manipulate the code that we are actually executing in our web application. And this is sort of a counterpart to vulnerable and outdated components when we have a component that is maybe not malicious, but has a vulnerability in it because the developer of it made a mistake. Here we are talking about someone intentionally messing with our code and injecting some evil code that our application is going to run. So we are dealing with these issues by ensuring the integrity and authenticity of both data and code. And this category is very important because of a recent surge in software supply chain security issues. There were quite a few of these making the news. SolarWinds was a big one in the United States last year, which basically compromised all of the computers in their government that used this particular software, because attackers managed to compromise the CI/CD, continuous integration and deployment system used by the developer of that software. And this is kind of a DevOps adjacent topic because we are talking a lot, as I mentioned, about CI/CD, software updates, and making sure that the code integrity is maintained. And there are, of course, many other issues that can compromise the integrity of an application, such as, for instance, failing to protect the integrity of cookie data. One of the vulnerabilities that was actually new on the OWASP Top 10 2017, which was insecure deserialization, got merged into this category as well, and it demonstrates how code integrity may be broken as the consequence of deserializing a malicious file. So let's talk a little bit about that and insecure deserialization as a topic by itself. First of all, just a few words about why deserialization is dangerous. There may be scenarios where we need to save the state of a particular object into a file or other kind of stream, or send it across the network to another component, which can then recreate the object that we have on our side. The process of turning this data stream, so a file or a protocol message, back into an object is what we call deserialization. Sometimes unmarshalling is also used for a synonym of this term. Most deserializers do this by creating a new object of the appropriate type, then setting the fields of this object directly through tricks such as reflection. Some common formats for serialization are XML and JSON, though in this case, we are going to be looking at Java class serialization. But keep in mind that a lot of it applies to basically any programming language that uses any sort of object serialization or deserialization. The main danger is that if we deserialize a malicious stream that was created by the attacker, we can potentially cause some very unexpected events to happen. So let's take a look at this scenario. Let's say that the attacker is able to create a malicious stream of some type. Basically, let's say that if we are deserializing from a file, then they will create a file which looks like it's a normal serialized object, but when we deserialize it, it is going to instead execute some code that benefits the attacker. And if we take a look at this in practice, we are going to be using a tool which is called Why So Cydrill, named after the Batman and Joker movies, I believe, where in particular, we are going to generate a malicious stream which executes some code when deserialized. So we are going to be exploiting the fact that due to how Java deserialization works, there is a particular class in a Groovy library in particular, which can potentially execute a command line when it's deserialized. And there are many, many other classes that can have similar behavior. So if I just go here and run this example here, and I will just say that I want this program, want this object that I create to execute a command line which starts the gnome mine program, which is the minesweeper program. Then what I'm going to do is that basically when I created this serialized stream and save it to a file, and when I deserialize this particular file, then as the result of the deserialization, the program will start. So this is definitely not what should happen, because when we deserialize an object, we just create an object in our program. It should absolutely not start an arbitrary process or even do anything else outside our program. But again, attackers can exploit this functionality. But okay, this looks a little bit theoretical because, I mean, we created this for ourselves. So let's take a more practical example. Let's say that we have a website which works just like Airbnb or Booking.com, where people can basically register their own properties, and then people can basically sign up for these properties because, well, they want to spend a few nights there, for example. And of course, in order to have a valid rating, we have something called a certificate of quality, which is some sort of data which is verifying that the rating of this property is what they say it is. So if I press this button, it is going to run a process which verifies the rating of this property using the certificate that I have uploaded together with this particular property. But the problem is that the certificate file itself is a serialized file because, I mean, it represents a program object, so it has to be serialized into a format that I can read up from my program and turn it back into an object. So if the attacker can create a malicious object, just like the one we have seen before, and remember that the file itself is not protected at all. The signature that we see about the rating of this property is within the object. The object file itself can be anything that we want. We are not protecting the object, we are just protecting the data inside the object. So the attacker will create a completely different kind of object, and abusing that, they can force our application to execute arbitrary code. So let's take a look. I'm going to log in here as the bad guy, as the attacker. And I'm going to add a new property. I'm going to call this the evil hotel. And I'm going to choose for this certificate of quality, the COQ, a malicious file that I have created beforehand. And when this malicious file is processed by the server, it is going to change the code of the web application itself. So I'm going to open it here and create. You can see that this is the command line which is executed. I'm not going to go into detail about this. Those of you who are more familiar with the command line tools in Linux can probably tell what's going to happen here. We're basically going to add a line to the main page of the web application that just prints out that the page has been hacked. So if I check the certificate of quality that I just uploaded, it's going to fail, of course, because I didn't upload a correct certificate. But it doesn't matter because just the process of trying to deserialize the object that I uploaded has triggered the code execution. And if I go back to the main page, I can now see that the code of the code of the page has changed. And if the attacker wanted to, they could do whatever they want on the operating system. They could start a server, they could do whatever they like. So this is like a demonstration of how this kind of problem can happen in the real world. So let's get back to the OWASP Top 10. So this was an illustration of something that was kind of new on the Top 10, or rather a part of this new category. Then we have the last new item on the OWASP Top 10 called SSRF, or Server-Side Request Forgery. Unlike the other new additions that were large and broad categories of security issues, this is a specific vulnerability. It is not new. This problem has been known in 2008, but it's becoming increasingly important with the levels of indirection present in modern web applications, especially in the cloud. So let's put simply, SSRF, short for Server-Side Request Forgery, is a vulnerability that occurs when the web application fetches a resource from a user-provided URL without validating it properly. By exploiting this, an attacker can force the web application to make a request to either another server on the internal network or read files from the local file system, and sometimes even execute arbitrary code on the server. All three of these problems are subsets of the SSRF vulnerability. And the reason this vulnerability is so important, because it's a very good example of a vulnerability that bypasses many of the security measures that a lot of companies think is how we should protect against attackers, by using firewalls and intrusion detection systems, because the attacker is basically forcing the server to make, which is trusted, the server application is a trusted program, to do their dirty work for them. Of course, there are many more than 10 security issues that threaten web applications. OWASP recognizes this too, so they have an 11th element on the list that identifies 3 broad areas where critical vulnerabilities tend to be found. The first of these categories is code quality. And yes, these are only listed as number 11 on the OWASP Top 10 if you are looking at the list. The first one is code quality, which is various language-specific mistakes that lead to underperforming and non-robust code that can be either exploited by an attacker directly, or maybe they will just make the job of the attacker easier. The second one is denial of service, specifically vulnerabilities that can allow an attacker to consume some sort of limited resource on the server, like a CPU or memory, or just cause the server to crash or lock up. Or sometimes even just flooding the target server with a ridiculous number of requests can be enough. Finally, memory management is a category that goes beyond web applications. Even though web applications are typically written in so-called managed languages like C#, Java, Python, Ruby, and JavaScript, where you don't have direct memory management exposed to the programmer, they still use native C or C++ components under the hood for this purpose. And if an attacker can exploit any of these components through the web application, they can potentially achieve direct code execution in several different ways, such as by exploiting a buffer overflow or use after free vulnerability. So these vulnerabilities are specific to C and C++, which is probably not the language you are working with, but the components that you are using probably use some C or C++ code very deep inside. So let's take a look at an example of a denial of service vulnerability in a code that affects any web application that uses regular expressions provided by the user. So we'll look at this in Java, but this problem is not language specific. In fact, it's a little bit easier to exploit it in other languages than Java. So let's take a look at this one. And in this one, we'll take a look and see how regular expressions can be exploited. So let's say we have a situation where the attacker or the user can specify part of a regular expression. Let's say that we are creating a search engine or something, and we are using a regular expression to search for the data inside our database or something, and the data that we are searching for is provided by the user. So this is a very simple program. It basically just looks for a regular expression inside the string which is specified by the user. So I'm not going to do a full introduction of regular expressions, but A+ basically means any number of A characters. So if I create a regular expression that says A+, that means I'm looking for a string that only has A characters in it, and it has at least one of them. And then I add as an input a string which has a lot of A characters, and then something which is not an A character, like an X character at the end. So obviously this is going to fail. So then what is the problem? The problem is that the attacker can exploit how the regular expression parser actually works in the background. They can create a regular expression which takes an exponential amount of time to evaluate for each character that is in it. So in this particular case, I can create a regular expression like this, which is basically says that I am looking for any number of A characters as a group, and then any number of those groups, any number of times, any number of times. You can see that we have multiple levels of references in here. And the problem with this is that if I create a long enough input, and of course I make sure that the input doesn't match what I'm typing, the evaluation of this regular expression is going to take a long time. In fact, it's an exponential problem. It is going to take basically every character in this input is going to double the amount of time it takes to evaluate this regular expression. And we can see that the CPU is basically completely used up by my web application because it's trying to evaluate this regular expression. It's going to keep evaluating this until the end of time. So this was a demonstration of how regular expressions can lead to a denial of service problem. And this is, by the way, not a bug. This is not a bug in the regular expression library. This is a problem in how the developers use it. So in here, the mistake of the developer was that they allowed the attacker to manipulate what the regular expression is in the system. And of course, there is much more to say about regular expression denial of service, but as an introduction, this is good enough. Okay, so to close off this discussion, let's talk about this new OWASP Top 10. What's its direction? What's its future? And how is it useful to us? First of all, the first question that a lot of developers may have when they look at this list is it still useful? After all, there are a lot of generic things now on the OWASP Top 10, which didn't used to be the case. The OWASP Top 10 used to be just 10 vulnerabilities, basically, but as we can see, it's now changing like slowly into this list of categories, which are very broad. After all, we are including design issues, which is not even for programmers. And the loss of specificity doesn't help developers in knowing what specific things to do to protect themselves from these weaknesses. And some of the low-hanging fruits are not hanging so low anymore. So this is true, but it's also intentional. The top 10 is not supposed to be a checklist for compliance, remember. It is supposed to be a starting point. And the categories are broad, that's true, but each of the categories is still anchored to specific issues through CWE, as I mentioned before. So if a developer wants to know what are the security issues in this category, they can still know it. There are just more of these issues than there were before. Developers can still follow these connections to find out what specific issues to look out for when, let's say, they're implementing authentication or authorization. One area that's definitely impacted by the new top 10 is the security industry. It's moving away from concrete problems. It's becoming harder and harder to create tools or methodologies that offer full coverage of the top 10. Creating a tool which is testing for XML external entities or XXC is easy, but creating a tool that can assess a program for design flaws is not really feasible. So this is actually, in the long run, kind of a good thing, because it will disincentivize chasing the top 10 as a motivator for security companies and force a more holistic view of software security instead of just saying, oh, just solve these 10 problems and then your code is okay. Now let's look at the effect of the top 10 when it comes to learning about security. Of course, as training companies and the companies involved with training, we are a bit biased here, but the new top 10 is looking pretty promising because the coverage of weaknesses is greatly expanded and offers a more consistent way to introduce long-standing higher-level problems like secure design to developers. Because after all, if something is in the top 10, you cannot really have any excuse for not looking at it. We must talk about them no matter what. So this is actually a good thing. And that is exactly what we do, since we have already adapted our material to fit this new top 10 and provide full coverage of all issues, both the old problems under new names and these newly introduced categories. And of course, remember when I mentioned that there are those 3 areas that were mentioned as the next steps in the top 10, the memory management problems, the denial of service problems, and the code quality problems. Those are also things that we are basically already covering through our training courses. So how does it all work? Well, let's take a quick look. In general, in our courses, we are trying to follow a very certain path. Instead of just having slides that talk about the problem and the theory, we try to have practical exercises. You have seen a few of them here, where the participants can get first-hand experience about how a particular security problem looks, how it can, like vulnerability can be triggered, and what the consequences are going to be when someone exploits a problem. And more importantly, after looking at the hacking part, we also talk about how to solve these problems. So the next step, of course, after talking about decentralization is, well, how do you solve that problem? And then we talk about the solutions. And in most cases, we also have interactive lab exercises for that. And another important thing is to make sure that we anchor a lot of these problems to real life issues and not just problems that are, let's say, theoretical. It's very important to present real life case studies for this. And that is also something that we are doing. And yeah, this is all a gamified process, as you have seen, controlled by the Cydrill Sergeant, which is embedded inside the development environments of whichever programming language we are talking about, whether it's Java, C#, Python, Ruby, or C and C++ for lower level code. So Visual Studio, IntelliJ IDEA, or Visual Studio Code as some examples for IDEs. And of course, our partners in Northern Europe are Tieturi and Informator for Finland and Sweden, respectively. So if you are interested in any of these courses, feel free to check out the links that we are showing to you on this slide. And we are covering a lot of different languages. a lot of different areas, a lot of different worlds within security, such as automotive, healthcare, machine learning, banking and finance, with all of the specific requirements and specific security issues that are closest to that specific domain. And of course, we are also looking at different aspects of application security, web, of course, but we are also covering Internet of Things, embedded systems, and general application security or desktop application security as well, both for developers, testers, and architects.